y'all, and welcome back to Linear Algebra with me. Today we're talking about subspaces of Rn, and what that's going to mean is we want to take a set of vectors in Rn and see what it looks like in Rm, where Rm is smaller than Rn. So for instance, recall we had two vectors, and the span of two vectors, which would be all linear combinations, ends up looking like a plane. So that's way back pictures from last week. But hopefully you remember, I want to look at two vectors in particular, say E1 and E2. So blue is E1 and red was E2. Then the span of those guys would be the entire XY plane. This looks like R2 because the XY plane is R2. What we are not going to say is span of U and W equals R2. We are not going to say that because it doesn't equal R2. Why is that? Because U and W were not in R2, they were in R3. So what can we say about that? Well, we have something called subspaces that we haven't talked about before, and we can say that they are a subspace of R3. And then same thing with this plane back here. It's not just R2. This is kind of like R2. He's had a little bit of a lift here and a little bit of a tuck over here. And so it's like R2's close cousin, we'll say. And he's also a subspace. So let's get a formal definition for subspace. So a subspace of Rn is a collection of vectors V, and all those vectors are in Rn such that we get these three things. We want zero, we want addition between vectors, and we want to be able to multiply all those vectors and have all those things still be in V. For example, span is going to be a great example of a subspace, where we're going to have it's equal to V1 to VP. And I guess I should say that these guys are in Rn, and the span is going to end up being a subspace of Rn. Let's check. Let's verify this real quick. So 0, it needs to look like a linear combination of V1 through VP in order to be in the span. Well, if we just pick the linear combination to be the coefficients are all 0, then we're good. It is in the span. So then linear combination will be in the span, so then 0 is in the span. Number 2, if we have two vectors that are in V, we want to get that the addition of these two vectors is also going to be in V. What we know is that U has to look like a linear combination of the vectors that are there because U is in the span. And then same thing for W, but he's a different linear combination, so we'll give him coefficients B. So we put this together, we do U plus W, and you end up getting just the coefficients add together. This is another linear combination because this is just a constant and a constant. And so this linear combination is going to be in V, which means U plus W will be in V. Number 3, we want to be able to multiply by a scalar. So here we go. So that will be C times A1 all the way up to the pth term. Once again, constant, constant, so it's just a linear combination. Linear combinations are in the span. So then C times U will be in the span. So there we go. The span of some vectors is indeed a subspace. Some more examples. I've got just the set of the 0 vector is a subspace. Well, let's check. 0 is indeed in V. Done. We've got U and W are in V, but the only things in V is 0, so that means that U equals W equals 0. So then U plus W, guess what? It's still 0. So then 0 is in V, so U plus W is in V. And then number 3, C times U. U has to be 0. C times the 0 vector is 0, and that is in V. So it's not particularly interesting, but fun fact. Example 3, we've got Rn is a subspace of itself. Rn definitely has the 0 vector. If any two vectors in Rn can be added together to get a vector in Rn. And if you take a constant times a vector in Rn, you're still going to get a vector in Rn. Done. Okay. We'll say intuitive. And then what isn't going to be a subspace is going to be some line that is not through the origin. So, for instance, in R3, if you've got a line doing this, this guy is not going to be a subspace because the 0 vector isn't going to be in here. And it's not in there. So that is not going to be a subspace. If it was going through the origin, now we're back at span, that is a subspace. Okay. So we're going to move on and we're going to talk about very important subspaces that are going to relate to our matrix A. The first one we're going to do is called the null space of a matrix A, which is denoted just null with one L, not two. We were too lazy to keep both of them. And it is the set of all vectors such that AX equals 0. Yes, we have seen AX equals 0. That is the homogeneous problem. So we can rephrase this definition to be null A is the solution set to the homogeneous system AX equals 0. Why is it a subspace though? Let's check. Is this a subspace of Rn? Okay, so 1, we have A times the 0 vector equals 0. So we've got the 0 vector is indeed in null A. Cool. Number 2, we've got two vectors x1 and x2. They are in null A. So then we want to know if the result will be in null A if we add them. So we're going to multiply the sum of those two by A. Then we can distribute A and then what do we do from here? Well, we use the fact that A1 and or X1 and X2 were in the null space to begin with, which means the results have to be 0. So there we go. We got down to 0 because that's what it means to be in the null space, is to get the result of 0. So then X1, X2 gonna be in the null space. And then number 3, we want to be able to multiply. X1 is in the null space, and C is going to be a scalar. So then C times X1 is going to be multiplied by A, and hopefully we'll get 0. We can use properties of matrix vector multiplication to pull that C out to the front. So C times the 0 vector, and that will be 0. So then C x1 is in the null space as well. So yes, null space is a subspace of Rn. Next space we're going to talk about is the column space of an m by n matrix A. We call that col A. That one makes more sense. It's been abbreviated a little bit more, and it kind of explains why we only stopped at 3 letters for null space. And it is the subspace of Rm spanned by the columns of A. So we can rephrase that as col A is the set of linear combinations of the columns of A, which we can rephrase that again. We know linear combinations is the same thing as solving Ax equals b. So col A is the set of all b's such that Ax equals b is consistent. So let's do an example. Let A equal this matrix. Can we find the null space and the column space? We sure can. We're going to start with null space because it's easier. So 2, -1, 3, 0, 3, 4, 4, -5, 2. Oh. We're solving the homogeneous system. So we put zeros on the right-hand side. Okay. I went ahead and I switched the first 2 rows. Let's do it. We'll do R1 switched with R2 first. So -1, 3, -5, 2, 0, 4, 3, 4, 2. There we go. And then we're going to do, we're going to get rid of this guy. So that's going to be R2 plus 2R1. Okay, so that's going to be row 1 stays the same. Row 2 changes. And we get this. And then I'm also going to do get rid of 3 at the same time. So R3 plus 3R1. And we get 0, 13, 13. And then I'm going to take a moment and make everything pretty. We're going to do a -R1. Oh, blue. Be blue. So -R1. And then we're going to divide row 2 by 6s and divide row 3 by 13 all at the same time. So that's going to be -1, 3, -5, 0, 1, -1, 0, 1, -1. That's 0, 0, 0. And then row 3 is definitely being killed by row 2. And then I also want to get rid of this 3 here in the top. So that's going to be row 1 minus, oh, I forgot to do my negatives because I multiplied that top row by a negative. There we go. Now I've negativified him. So plus 3R2 is what we're going to need then to get rid of them. Okay, so row 3 turned into zeros, row 2 stayed the same, and then row 1 is going to change. That's going to be 1, 0, 2, 0. Okay, so then let's translate this back to system of equation style. Give myself a little bit more room. There we go. Okay, so then the solution vector looks like that. But I didn't ask to find the solution, I asked to find the null space. So let's write null of A is equal to, and we'll do it, the set of these vectors where x3 is anything. But we know how to write that using span, and so I'm going to write it using span. There we go. So we have found the null space of A. Now let's do the column space. By definition, we have what? We have col A is just the span of, let's see, the columns of A, which was 2, -1, 3, and 0, 3, 4, 4, -5, 2. But is there a more interesting way to like talk about this? Because that doesn't really seem that enlightening. The answer is yes. Remember from our rephrase. So from the rephrase that I gave you is col A would be the set of all the B's such that AX equals B is consistent. Okay, so I could go after what's going to be consistent for this system of equations. So let's go ahead and do that. Let's pick an arbitrary B, B1, B2, B3. And we're going to put that on our right-hand side. So that's going to be a 2, -1, 3, 0, 3, 4, 4, -5, 2, and then B1, B2, B3. There we go. And what I'm going to do is I'm going to do a different row reduction than before, not because you have to, but because I always like kind of like shortcut stuff, and I'm like, see, it's the same, it's the same, it's the same. You don't have to do it. There's not one way to do it, basically. And so I'm going to make you watch me do it not the same way. There is more than one way to do this. So I'm going to divide the first row by 2, which is a different way to get a 1 into that first spot. There we go. And then this way that I saw second is actually, I think, fewer row operations than the way I did before. Okay, so now we can take out this guy by adding row 2 and, I'll keep my red. Row 2 plus row 1. And then I can also get rid of this guy by doing R3 minus row 1. Oh, 3 times row 1. Okay. So row 1 will stay the same. And everybody else is about to get a little bit of a crazy change. Okay. So row 2 ends up being this. Not too bad. And then row 3 ends up looking like this. Okay. And then I'm going to do a division by 3 for row 2 and by 4 for row 1 or row 3. Because I don't like those numbers at all. And now the right-hand side doesn't look particularly wonderful, but it's fine. And 1/4. Okay, well that's not beautiful, and it's about to get less beautiful as we're going to do our last row reduction. We're going to get rid of row 3. Row 3 minus row 2. And then now we have row 1 is staying the same. Row 2 is staying the same. And then row 3 has been killed off except for the right-hand side, which is huge at this point. There we go. Okay, so why did I do that again? Because I'm looking for the column space. And how do I find the column space? I need to find all the B's that are going to make me have a solution. Okay, we know how to do that. We know that if this bottom row has a pivot point there in the right-hand column, we don't have a solution. So in order to have a solution, we need that to be 0. Okay, that's the new goal, is we want this terrible thing to equal 0. We can do that. And then I'm going to tell you right now, let's not even try dealing with the fractions. If you multiply it by 24, it's going to clear out everybody. Why 24 and not 12? Because you've got this 2 sitting on the inside. So if you did distribute that 1/4, it would end up being an 8. Okay, so that's going to be 6b3 minus 3/2 b1 minus 8b2 plus 1/2 b1. I will play with this. We can deal with this. 6b3 minus 9b1 plus minus 4b1. Okay, and then combine like terms, these guys, and also multiply by a negative so that I have a 13b1 plus 8b2 minus 6b3 equals 0. This is a plane. It is the b1's kind of like x, b2's kind of like y, b3's kind of like z, but this is most certainly the equation of a plane. So then we're going to say the call space of A is equal to all points b1, b2, and b3 such that they are on this plane. All right. Well, that's more informative than the span. It was not great to get to, but it was more informative. Okay, so we've talked about null space, we've talked about column space, and I'm going to take us back to linear maps. So what do null space and column space mean when we're talking about T with standard matrix A? First, let's go after the null space, because that's the easy one to deal with in my opinion. So null space is equal to all the x's such that ax equals 0. And now ax is the same thing as t of x, so let's rewrite that. So all the x's such that t of x is equal to 0. And then we actually have a name for that. It's called the kernel of T. You might remember this from homework 1, problem 5. I made you do some stuff with kernel of T. Now we know where it comes from and why it was important, because it relates to all this subspace stuff. And here's our formal definition of kernel. Oh my goodness, I spelled it wrong. Oh, I always do that. I write it with an A, and then I hit backspace and write it with an E, and sometimes I don't catch it. The kernel of a linear map T, denoted kernel T, or ker T, is the set of all vectors such that T of x is going to be equal to 0. Okay, so that's null space. What about the column space of A? So that was all the B vectors such that AX equals B is consistent. And then we're going to rewrite this using a T instead. So this is going to be all B such that T of x equals B has a solution. And then that's called the image of T, which I'm not going to give you a definition because I already told you what the definition is before when we first talked about linear maps. Image of T is something we've already done. We just now have that it's the column space of A. Okay, so just to clarify, notes about our vocab today. Matrices have null and column. And mappings do not. We do not talk about null and column with mappings. We talk about kernel and image. So functions are going to show up a whole lot more than matrices going forward if you do like analysis or abstract algebra and stuff. Functions are all over the place. Certainly been dealing with them much longer than you have with matrices. So terms like kernel and image are going to come back over and over. Null and column, not so much. If you do some numerical stuff or more linear algebra, you'll see it again. But kernel and image, keep track of those. They're coming back for you. And with that, I think that's all I've got for today. So I'll see you next time.